Let's start recording. So this is the outline of this chapter. We first will try to introduce magnetic field, B field, cross fields, and then we'll talk about the cross field, which means that we have E field, uniform E field, and uniform B field perpendicular to each other in a space. So this it tells you about the discovery of electrons and the Hall effect, which is an experiment to show the moving particle in the conductor should be negative charge, not a positive charge. So this is a hint that there should be electron moving in the electron rather than positive charge. Okay, and then we'll talk about the circulating charge particle, and then the cyclotron, synchrotron, which is something like the particle accelerator. And then we'll talk about the magnetic force on a current carrying wire, and then talk on a current loop, and then dipole moment, magnetic dipole moment, similar to the electric dipole moment. Yeah. Okay, so as I mentioned, magnetic field in this textbook, we all the way use the magnetic field to stand for the B field, but precisely speaking, it should be magnetic flux density. Magnetic flux density. If you're interested, you can just find it on the Wikipedia. There were plenty of information about this. So precisely speaking, it should be magnetic flux density, something like the electric flux, and then the density of the magnetic flux here. But the textbook here refer this to be the magnetic field because actually, precisely speaking, it should be the H field, but in this textbook, it does not use H field at all. So yeah, so that's fine. Maybe. So in some cases, use magnetic field to refer to the B field might be okay, not so rigorous, but actually it will be fine because there only is a ratio between them. So we don't bother. I don't really bother to change all the magnetic field to be magnetic flux density. Okay, so a magnetic field can be defined to be a vector quantity that exists when it exerts a force Fb on a charge moving with velocity v. Okay, so v is directly perpendicular to the force Vb, and then the magnitude of V can be defined in terms of the force magnitude. Okay, so when we only talking about the magnitude, it is still fine, which means that if we assume the magnetic field with a magnitude B, and then the force divided by the charge divided by the velocity will be this magnetic field. Okay, so this is different from the Coulomb's force. For the Coulomb's force, it is like F equals 1/4 pi epsilon naught times Q1 Q2 over R squared. It doesn't relate it to the velocity of the charge at all. It only related to the charge amount and the distance between them. And this is for the Coulomb's force. But for here, we can call it the magnetic force. Yeah, but actually in some sense, we will generally call it the electromagnetic force by adding them together. So which is like, or somehow we can write it as Q times E, something like that. So this is the magnetic field multiplied by the charge multiplied by the velocity. So the main difference is that the magnetic force related to the velocity of the charge particle. Actually, also related to the direction because we only count the component which is perpendicular to the magnetic field. And of course, the magnetic field is a vector field like the electric field. So where Q is charge of a particle, we can summarize all this result with the following vector equation. Fb is QV times B, QV times B. Not times. This is the cross product. Sorry, this is the cross product, which is the difficult part here. Of course, I think you should learn it in high school, physics, but still, it is not an easy concept here. So the first law, the force, the Lorenz force. Here we call it the Lorenz force. Fb is on the particle by the field. B is equal to the charge Q times the cross product of its velocity and the field B. So measure in the same reference frame. Measure in the same reference frame. This is very important, although you don't really care about it. This is actually is related to the relativistic effect, but yeah. So yeah, I think for physics student, I actually don't really care about it, but actually we assume all the measure the field and also the velocity measure in the same reference frame, which means there are no we will talk about inertial reference frame later in this semester about when we talk about the special relativity. So we can write the magnitude Fb as Fb equals QVB sine theta, where phi is the angle between the direction of the velocity v and the magnetic field b. Okay, so here we have an equation, the vector form like this: Q times V cross B. Q times V cross B. So this is a cross product. And if we write it in the scalar form, Fb equals absolute value of Q, V, B times the sine phi. Phi is the angle between the velocity and also the vector field. Okay. So yeah, so maybe let's talk about the cross product first, the direction of the cross product. If you forgot what is the cross product, actually we will always use the right-hand rule. Right-hand rule. Right-hand rule. Or in short form, I sometimes will write it as RHR. Right-hand rule. Okay. So cross V into B to get the new vector V cross B. So Zoom is not good for presenting it because we can only see graph. You cannot see my demonstration. But yeah, probably tomorrow I can start to demonstrate it practically. So as you see here, if we have V cross B, then you use your four fingers pointing to the vector V. Yeah, V cross B here. Very important point is that for multiplication, for scalar multiplication, A times B equals B times A. But here, for cross product, if you if you swap the order of it, then there will be a negative sign. There will be a negative sign. Very important part here. You cannot arbitrarily reverse the order of the cross product. So here, V cross B. So the first one, you try to use your forefinger point to the direction of the first vector, and then you try to swap to the second one. And then you point to the second one, and then the direction of your thumb will be V cross B. So this is V cross B. And actually, this is the phi in the previous page. This is the phi in the previous page. And we also know that phi should be less than or equal, larger than or equal to 0, and then smaller than 0 degree, and not smaller than or equal to 180 degree. Yeah, so this is very important. You don't try to swing line the other way around. It should be like that. this angle is less than 180 degree and larger than 0 degree. Don't try to swing like that, which is larger than 180 degree, and then your thumb will point to the other way around. This is not correct. So you need to guarantee that the phi is between 0 and 180 degree, like that. Okay, so now we can know V cross B pointing upward, and then if FB, if Q is positive, if it's a positive particle, then the force will have the same direction as V cross B. If it is a negative particle, then then FB will have the opposite direction with the V cross B, like this. Okay, so yeah, so we use the right hand rule all the way. Don't try to use left hand rule, because you will have a negative sign induced here. Okay, so here we talk about the cross product. The cross product. So the cross product is like here. If we have V cross D, something like that. This is V, this is B, this is the angle phi. So this angle is between 0 and 180 degree. So you know V cross B should point to this direction. So the direction is fine, and the magnitude will be the area of this parallelogram. So in high school physics, when you learn the trigonometry, you know the area of this triangle is 1/2 V times B times psi phi for the triangle, the area of the triangle. So for the area of the parallelogram, bounded by this vector and this one is parallel with this one, and then this is the B, and then this parallelogram bounded by B and V, and then the area will be, the area here will be V times B. The area of the parallelogram will be V times B times psi phi. So this is the magnitude of the cross product. The magnitude of the cross product is actually the area of this parallelogram. So this is VB psi phi. How does it come from? So this is actually the geometric meaning of the cross product. And before we know the dot product, suppose we have A dot B. And if we take the absolute value, it will be like A times B cosine theta. Theta is the angle between them. So if we have A vector and B vector, this is theta. So it is like the projection of B on A. So this one will be B times cosine theta, cosine of theta. B times cosine of theta. This is the adjacent side. So B, this is cosine theta. This is B cosine theta. So B cosine theta times A. So this one is A. So A times B cosine theta will be the dot product. So which is like B with the direction parallel to the A, and then multiply them together. So this is the area of the parallelogram bounded by these two vectors. So if V is parallel to B, then V cross B. Then V cross B will have a magnitude of 0. If V is perpendicular to B, then V cross B will have a magnitude of VB, because sine of 90 degree is 1. Okay, so here we have a quick checkpoint here. So it asks, this charge is moving to the left side and the B field pointing downward. So it asks you each of the situation, what is the direction of the Lorenz force? Lorenz force. So for part A, V cross B, you use a forefinger pointing to the left side and then cross to the negative right axis. Then your thumb will point to Z axis, and this is a positive charge. So FB also point to the positive Z axis, like this, FB. Okay. Also V cross B. Okay, for the next case, V pointing to this side, B pointing to this side. So V cross B, your thumb will point to the positive x-axis. So this is V cross B. So this is a negative charge. So FB pointing to the opposite side. So this is a negative x axis, negative x-axis. And for part C, V and B point to the opposite side. So this is 0. This is 0. So no direction. Okay. So yeah, so let me talk about this. So we can represent magnetic field with field lines as we did for electric field. So yeah, so this is actually a magnetic bar, and then you can see the magnetic field line is actually similar to the electric field of the dipole, of the electric dipole. So if you still remember, for the electric dipole, the electric field line is something like this, like an apple, okay, something like that. So here you also seeing something like this, doing something like this, yeah, like this. Okay, so this is, yeah, so it has some similar property as the electric field line, so I don't repeat it here. And then you can see here, in the middle part is the magnetic field bar, and then you put in some iron fillings, something like powder form of iron, and then you put it there. Then the iron will follow the direction of the electric field line. Actually, the direction of the magnetic field, magnetic field line. So you can somehow see these are the magnetic field line. Of course, it is not complete because the iron filling is not enough, but generally they will touch the end of the magnetic bar and then will follow the direction of the magnetic field line. Okay, so let me finish this page. So two poles. For magnetic field, we can only see two poles to occur at the same time, which means that the closed field line actually the closed field line of a magnetic bar enter the other end. So the end of the magnet from which the lines merge is called the north pole and the magnet. So it's something like the electric field line. The electric field line also starts from positive charge to negative and ending at the negative charge. But here we only call it magnetic field is starting from north pole to south pole. Okay, so nothing special here. So here it says opposite magnetic poles attract each other and like magnetic pole repel each other, similar to the charge opposite charge attract and then same charge repel. So like that case. But the point here is that if you try to break a magnetic bar, even for primary student, you know that if you try to break the magnetic bar, it will form like NS, something like that. So you can imagine, actually this is so-called a magnetic dipole, is formed by many small dipole, and then when they are joined together, they will something like point to the same direction, and then will act as a single magnetic dipole, and then you try to break it, then it will still be a magnetic dipole. You can never find a magnetic monopole. 子弹体 as far as now, you cannot find that. If you're interested, you can find it on the Wikipedia to find the page about the magnetic monopole. So magnetism is a magnetic by an electromagnetic. Electromagnets is not caused by magnetic monopole, but for the charge, we can have positive charge, negative charge independently. But for magnetic dipole, we cannot separate into magnetic monopole. We cannot have north pole occurs independently and south pole occurs independently. So there's no known experiment or observation evidence that the magnetic monopole exists. So let us stop here today.